This is part 3 of Lab 16, which is JK flip-flops and D flip-flops or latches. We're working on the last part of this lab, which is where we're going to deal with the JK flip-flops. So what we've learned so far is the 7474 is a edge-triggered D-latch, edge-triggered latch. So what we say on this one, basic rule of thumb says Q, the Q output follows the D input on the rising edge of the clock because there is no bubble here. We also learned that the set, if we set a latch or preset a latch, Q goes to a 1. If we reset a latch, then Q goes to a 0. Okay. And we also learned this could be preset. And then Q, not Q, will always be opposite of Q unless we bring the set and reset lower at the same time. And this is what we call an ambiguous state. So we went through the truth table. Or I'm sorry, we went through this table. Then we went to the 7475. It's a 16-pin dip. This is where we moved our power pins over to pin 5 and pin 12 with the VCC on pin 5 and ground on pin 12. We learned that there's 4 of them inside this thing. It does not have a preset. It does not have a clear, but it does have an enable. This is a level triggered D flip-flop. On this one, we said that Q follows D anytime that that E is high or C on this guy. Now we're moving over to the 7476. The 7476 is a JK flip-flop, okay? And there's 2 of them in here. So what we're going to do now is you need to go to the data sheets on Blackboard, and you need to look up the 7476 and record the pinout. Now there are 2 JK flip-flops inside this thing. It's edge triggered on the low going edge. Actually, it takes a pulse, but we'll explain that in a second. Then we're dealing with, we're going to be wiring up flip-flop number 1, which would be pin 1, pin 2, preset. That means if we preset it, then Q will go to a 1. We got a low action preset. Here's clear for 1. Here's J1. It's a JK flip-flop. Here's K1, Q1, not Q1. This would be our common. And then the other pins belong to J2. But when you do your pin out, you're going to do your pin out for all of them that we're not using. So go ahead and pause your lecture. I'll go to the data sheets, and then, go to the data sheet for the 7476 and do your pin out now. Okay, now we're going to move to the actual circuit here. We're using a JK flip-flop number 1. So you need to go ahead and do your pin out on your diagram. Like I told you in the last section, I'm grading heavily on following these instructions because I'm doing the circuit. Okay. So what we're looking at is over here on the switches. I am connecting the reset or the clear. I'm collecting this to switch 0. The set or the preset, I'm going to connect this to switch number 1. Now, I'm going to correct this. So y'all need to mark out the 5 volts here because we are going to show y'all how these things work. This is what I couldn't understand because they told us to come over here and switch it low, but I think they meant jump it low over to a low. But we're going to hook it up to one of our switches. So S, or the preset, we're hooking that up to we're hooking this up to switch 1, and the reset or the clear, we're hooking this up to switch 0. The K or the J, I've got this connected to switch 2. The clock, I've got this set to one of my pulse switches, one of my debounce switches. I have this on the first one on the left. They don't give these numbers that I see. And then my K, I have this connected to switch 3. My Q output, I still have that. I'm using LED 7. My not Q output, I'm using LED 6. So I'm going to switch over to the camera now so you can actually see the circuit. So here's the 7476. Here's the power pin on pin 5. Here's the common pin on pin 12. Okay. And of course I have the J, K. Here we have the not Q going to, I'm sorry, we have the Q going to pin to LED 7, and we have the not Q going to LED 6. And then we have the presets and the clears. So here's my preset in clear. So they're both low active. So this is reset. This is set. This is ambiguous. This is my J. And this is my K. So what we're going to do, what we say about the JK flip-flop is on our synchronous inputs. Okay, it's just like the 7474. Your reset and your clear, these are asynchronous inputs. They are not timed. They have priority over the synchronous inputs. The synchronous inputs, we have 3 on this guy. We have the J, the K, and then of course it's synchronized with the clock. So I kind of misworded that. The synchronous inputs are the J and the K, and of course they're synchronized with the clock. Okay, so that's the clock input. So preset, and we'll look at this. So I'm sorry, wrong one. So this is going to reset it. This is going to clear it. Now what we're going to do now is we're going to go over and look at the truth table or the function table out on the data sheet. So here's the data sheet from the 7476, and it says, okay, if I bring the preset low, I have the clear high, then the clock don't care, the J don't care, the K don't care, Q is going high, and of course not Q goes low. If the preset is high and the clear is low, then the clock don't care. We don't care about the clock. We don't care about the J. We don't care about the K. Q is going to go low. So these have priority because these that here are don't care. If I bring the preset low and the clear low at the same time, it says, and the clock don't care, the J don't care, the K don't care. It says both the output goes high, and then it tells me to see note 1. It says this configuration is non-stable. It says this configuration is non-stable. That is, it will not persist when the preset and or clear inputs return to their active state. If we bring them low, try to bring them low at the same time, it's impossible for me to do. It could be done digitally, but if you brought them low at the same time, there's no guarantee how this thing will come up. Sometimes it would come up sad, and sometimes it would come up clear. Here, we're not presetting, so the next 4 items that we have, or the 4 steps that we have, preset is high, clear is high. We have a clock pulse. So for the JK flip-flop, you have to have, for a master-slave flip-flop, which I'm not going to tell you what that means, you have to have a pulse. So what we have to do is we have to have a low to high transition. So we have to go low, then when we go back high, so we're low, right? Then we go back high, that's when it's going to change. So we got to have both edges on this thing, both edges. So on this thing, it requires both edges. Okay. So high, we have a clock, and we have a clock pulse. If J and K is low, then this guy Q will equal to output. So Q will be, so this right here, this is latched. Okay, so if I want to latch it, I'll bring J to a low and I'll bring K to a low, but my preset and my clears have to be high. Preset and clears are high, I perform a clock pulse. If J is high and K is low, then this guy Q is going to go high and not Q is going to go low. Okay. If I bring preset high and clear high, I apply a clock pulse. If I have J low and K high, then my output is, my Q is going to go low and my not Q is going to go high. So to set it, using our synchronous inputs, I bring J high and I keep K low and I apply a clock pulse. If I want to reset it with the synchronous inputs, I bring K high and J low and I apply a clock pulse. Now look at the last one. It says if I bring both of them high and then I apply a clock pulse, it means it's going to toggle. It means my inputs are going to change states. So if Q was a high, then it would go to a low. If Q was a low, Q would go to a high, and of course not Q is going to be just that opposite. We did this with the D flip-flop, and that's why they call it a D flip-flop, but I had to take the not Q and feed it back into the D to cause that thing to flip-flop. This thing right here has a natural flip-flop, just bringing the J and the K high, and this then providing the clock pulse. So what we're going to do now is we're going to go back to our lab. And then we're going to perform, let me bring up, here we go. Sorry. So we'll go back to our lab, and then we're going to go through this truth table right here. Now notice what I've done on this, just to keep us from in sync, is I've numbered the steps on the left-hand side, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that's the way I'm going to reference them, so you can get your Q's and your not Q's set up exactly the way they're supposed to be. Okay. So what I've done on purpose is I've set the latch so we can see this first thing right here. So I'm going to go back over to my diagram. So we're going to start off with step 1. Okay, so right now I have Q at a 0 and not Q at a 1. So the first thing we're going to do is in step 1 is we're going to bring our set low, or our preset low, and notice Q goes to a 1, not Q goes to a 0. And I can come over here and flip these clock pulses all over the place, and notice nothing happens because the preset has priority over the synchronous inputs. Okay, so this is what happens. So that's step 1. Step 2, I'm going to bring set high, and I'm going to bring a reset or clear low, and Q went to a 0 and not Q went to a 1. Okay, what I'm going to do is I'm going to flip this. Here's my J and K inputs, and notice they are not affected because my asynchronous inputs has priority over my synchronous input. The next thing we're going to do is we're going to bring set and reset low, both low at the same time. Q and not Q goes high. That's the ambiguous state because there's no guarantee how this thing is going to come out. Notice it comes out different even when I'm flipping the switches, trying to do them at the same time. So there's no way in the world we're going to know how this is going to come out, right? And of course, if I change this, then it's not going to stay in that state anyway. So that's why they call it an ambiguous state. And this is something that what I found out over my years dealing with digital circuits, if an output is available to an engineer, they will use it. So you'll see this right here used sometime to generate both outputs to Q and not Q at the same time. So what we're going to do now is we're switching in to the next one. And what we're going to do is I'm going to go ahead and set it so we can see it change. So I set it with asynchronous inputs. So the next one says we're going to bring set and reset or clear and preset to highs. So I have them highs. So we're on step number 4. And then it says what I'm going to do is I'm going to bring the J and the K both low. And then we're going to come over here and pulse this thing, and nothing happens. It's latched. So I'm going to come over here now, and I'm going to preset it on purpose. And I'm going to bring both these low, and I'm going to apply a clock pulse. And you notice it stays the same. So step number 4, the Q and the not Q, we're not going to put this down. What I want you to do in step 4, I want you to put it's going to be latched. Because whichever way I put it in, if I bring the J and the K low, it's going to maintain that state no matter what the clock input does. Now, we're not going to fool around with the presets and the clears because these guys have priority over these guys, right? So what we're seeing what's going on over here. So the next step, step 5, I'm going to bring J to a 1, J to a 1. I'm leaving K at a 0, and then we're going to apply a clock pulse. And notice, so J1, K0, Q goes to a 1, and not Q goes to a 0. But I had to apply a clock pulse. So that's step 5. What we're going to do next is we're going to bring both of them low. I'm on step 6. And then we're going to apply a clock pulse, and nothing happened because we're latched. Then I'm going to go to step 7. Still have preset clears high. I'm going to bring K to a 1. I'm going to leave J at a 0, and I'm going to apply a clock pulse, and notice the latch clears. So Q goes to a 1, Q goes to a 0, and not Q goes to a 1. The next we're going to do is going to bring both J and K low. This is step 8. I'm going to apply a clock pulse, and nothing happens because the latch is latched. The next thing I'm going to do is I'm going to come over here, and I'm going to bring both the J and the K. I'm going to bring these both to 1s, and then I'm going to apply a clock pulse. And notice I'm going to keep going. I'm not going to stop because every time I apply a clock pulse, this thing toggles. So what we're going to do on step 9 is we're going to say toggle. Okay, so what we're going to do is we're going to go back and repeat the truth table just so you got it right. So what I'm going to do is I'm going to leave this thing reset. Okay, so we can see it set. So I'm going to come over here. I'm back at the top. I'm going to step 1. I'm going to bring set low or preset low, and the latch preset. My synchronous inputs mean nothing. Step 1, I'm going to bring reset low. Notice the latch went, Q went to 0 and not Q. The next step, I'm going to bring both these low. This is the ambiguous state, so Q and not Q both went high. You need to write that down. Next thing I'm going to do is I'm through with my asynchronous inputs. I'm going to move over to my synchronous inputs. What we're going to do is we're going to bring J to a 1. We're going to leave K at a 0. We're going to bring J to a 1 and K to a 0. Got that right now. Now we're going to apply a clock pulse, and it's set. So J1, K0, clock pulse, Q goes to a 1, not Q goes to a 0. Okay. Then we're going to bring both of them low. So I'm on step 6. I'm going to apply a clock pulse, and notice now it's latched. Okay, now I'm going to step 7. I'm going to bring K high and J. I'm going to bring K high and J low, right? You understand? And I'm going to come over here, and I'm going to pulse it, and it reset. I'm going to come over here and bring both of them low. I'm going to apply a clock pulse, and it's latched. That's step 8. And then I'm going to come over here on step 9. I'm going to bring both J and K high, and every time I apply a clock pulse, it toggles. So that is figure 16-6. So what I'm going to do now is I'm going to move over to figure 16-7. I'm going to pause the lecture, and this is all going to be on the last part. So y'all that was in class and we had problems with this last circuit, this would be the only part of the lecture that you will need to watch to complete Lab 16. If you are absent, of course, we've talked about this before, and I'll also put it on there. If you was absent when we did Lab 16 in class, you can go to the lab experiments, go to Lab 16, download that, print it off, and then you can start watching the videos, and then you can complete this lab. This lab is due on Monday, which will be the 22nd. And there is no grace period. Well, there is, but you'll lose points for every day that you turned it in late. Okay, so now we're working on figure 16-7. I could have left it connected like this and just turned all my switches up, right? But unfortunately, I already tore it down, so I have actually rewired this circuit. So I have all these pins right here connected together. You need to go ahead and do the pin out. You can transpose the pin out from figure 16-6. Of course, here we are actually connecting these to 5 volts. But remember, 5 volts is 5 volts. So I have this pin connected to this pin, connected to this pin, connected to that pin, and then all those pins are connected to 5 volts. Now what we're going to do is I have my clock pulse out, but remember, when we hook up J and K, when they're both at 5 volts, then what happens? Well, what happens is the Q output toggles. Now, what I'm going to do is I've got the Q still. I still got the not Q up here. And instead of using the 10 kilohertz clock, which they're asking us to use right here, I've got this hooked up on about a 1 hertz clock, but it's really, really slow. So we can actually see it toggling, but now it's toggling off the clock. So what I've got, I'm going to switch this back over to my camera so we can see the circuit. So here's the circuit, and what I've done is I've taken the clock input, which is pin 1, which is right here. Sorry. My camera's froze. Hold up. I'm going to pause this. So I have it working now. My camera froze for some reason. But what I have is I've taken my clock pulse, which is pin 1, and now I have it running over to the digital clock output of the trainer, and I have it set on 1 hertz. And you see what it's doing. It's just toggling. Okay. So to keep from getting confused, well, I'll leave them both up here. Now what we're doing, according to the lab, I'm looking at step 7. And step 7 tells us to apply a 10 kilohertz clock to the input. Now notice these lights appear to be on at the same time, but they're not. This works very similar to what fluorescent lights do that's in our classroom. When we look at a fluorescent light, it appears to be on all the time, when in actuality, the fluorescent light is turning off 120 times a second every time the AC input goes to 0. But what happens, it's doing this every 8.33333 on milliseconds. And our eyes, the persistence of our eyes blends that together. So what that means is the cones and rods in our eyes don't have time to respond. And thank goodness, because if we could respond that fast, we wouldn't be able to watch TV. So TV is a series of individual pictures that's being flashed on your TV. But what happens, it appears like they blend together because they're doing it at a rate, we call it a refresh rate, that you just can't comprehend. And in fact, the refresh rate on most TVs is around 60 to 100 hertz. Which is basically the same thing that Alabama Power is using. So these lights are actually flashing. We can see this when I move over to the oscilloscope. So here's a circuit. Like I said, I could have left it all hooked up to my switches and just flipped all of them high. But unfortunately, I tore it down before I noticed, because this is the actual circuit. So what I have is I have my 5 volts coming into pin 5, and then I have all these pins jumped to pin 5. So they're jumped up to pin 5, so that means we're not preset and we're not clear. But what's important is J and K. J and K are both 1, so every time it toggles. So what we're going to do now is I'm going to move over to the oscilloscope. So this is the oscilloscope. I have my setting on 50 microseconds per division. It's kind of hard to see. So this is my clock input coming out. So I'm coming over here. I've got 50 microseconds per division. So that's 100 microseconds for 100 microseconds for 1 pulse. So if I come over here and bring up my calculator, and then to go from time to frequency, we take the reciprocal of time. So that's 100 microseconds times 10 to the minus 6. Then I'm going to take the reciprocal of that, which is right here, and it says that's 10,000 hertz, or 10,000 or 10 kilohertz, which is what we're supposed to be setting at. So my scope is set up to draw it just like it is in your lab. Okay, and we're looking at, and that's what they're showing us down here. So my time would be 100 microseconds. We just measured that on the scope. So we could use the calculation to actually set the scope up. So let's bring up our display full screen again. So this is what I want to show you. So here's 1 cycle. So negative to negative, that's 1 cycle of the input. And here's 1 cycle of the output, negative to negative. So over here, it's taking 1, 2, 3, 4, twice as long. Twice as long. So that's 50 microseconds per division. So this would be 100 microseconds, 200 microseconds. So if we come over here and pop our calculator back up, and I enter 200 microseconds, 200 times 10 to the minus 6, and I take the reciprocal of that, it says 5 kilohertz. So when we do this, when we set up the input to toggle, my Q output is going to be exactly 1/2 of the clock input. So in this situation right here, my clock input is running at 1,000 kilohertz. 10 kilohertz. And my Q output is running at 5 kilohertz. So the JK flip-flop, when we set it up to toggle like this, then my Q output will be exactly 1/2 of the frequency I applied to the clock input. So it divides by 2. So what I'm going to do now is I'm going to pause the lecture. So this takes care of 16-7. And then, and remember, you got to figure this out, right? You understand that. So make sure you give me the time for the bottom one. Let's see so let's draw this. I'm going to bring it back up. So what they're doing is they're showing 2 pulses of the clock, and they're showing us, this is 1 cycle for the clock. For every 2 cycles of the clock, then my Q output would give me 1 cycle. So I'm going to get you started on this to make you sure you understand what's going on. So I'm going to come up here and change my color. Let's do it in red. So here's my clock input. Of course, the data sheets calls this clock, and of course we're using clock 1. Then what we're going to do is we're bringing our Q output. So our Q output is going to start off at a 1. We can start it off at a 0, right? You understand that? Oops, I messed up. So my clock output for every 2 cycles, so here from negative to negative, this is 1 cycle. So from negative to negative, this is 2 cycles. What happens is my Q output would come over here and do, we're going to align it up with the bottom. So my Q output would come over here and do this. And then it would go back to 1 and go back Q. And you have to do the not Q. So remember, the not Q is opposite of the Q, and you got to go all the way across with this, guys. Okay? So there it is. So we figured that out. So for my output frequency, which would be this guy, it's not going to be 10 kilohertz. My output frequency, my time is going to be what? 200 microseconds. And then, of course, that's going to equal to a frequency in our situation of 5 kilohertz. And like I said, the drawing on the Screencast-O-Matic is not really good, but it's okay to see what's going on. Okay, so what I'm going to do now is I'm going to pause the lecture, and I'm going to move over to figure. I'm going to move back over to figure 16-3, and here we're going to go up. And so notice on this figure right here, so on this figure right here, what we're doing is I'm going to take my and we're going to move over to flip-flop number 2. So you need to do the pin out on flip-flop number 2, okay? Flip-flop number 2, we're going to do the pin out on this is going to be JK flip-flop 1, which we already have wired up. So instead of taking my Q output and running it up to my 7-segment display or up to my LEDs, I'm going to take my Q1 output and I'm going to bring it into the clock input of the number 2 latch. So go ahead now and pause this, go back to your pin out that you did back in figure 16-5, and go ahead and record the pin out for this JK flip-flop right here. Now, if this guy divides by 2, then we're taking the output of this and feeding to this, then this is going to be a divide by 4. So, but from the input. So if this is running at 5 kilohertz, we should expect this to run at 2.5 kilohertz. I'm sorry, 2.5 kilohertz. If I took the output of this one and ran it into another one, then that would be a divide by 8. Then we'd go 16, 32, 64. Now, what I want you to understand is we're going to show y'all something really, really neat when we look at the Q output. So what I'm going to do is I'm going to bring the Q outputs out of these things, and I'm going to swap them around so you can see. So we'll do a little more on this than what the lab actually calls for, because this will give us a lead into our counters. But these guys are frequency dividers. So if I keep feeding these, the Q output of one and feeding it into the clock input of the next one, every time it's going to increase by the power of 2. So 2 divided by this would be 2 divided by this. This would be 1/2 of that. And then this would be 1/2 of that, which would give us a divide by 4. And then the next one would be a 1/2 of that, which would give us a divide by 8 from the input. So this is what we're dividing right here. And I think I told y'all that since the fastest speed that we run our I/O buses on the compatible computers is 166 megahertz. So you might have wondered, and this is what I explained to the class the other day, is why all these gigahertz that they're talking about, all the gigahertz for the AMD and also the IBM and the other computers are always divisible by, if you multiply it by, they're always divisible by 166. So all they're doing inside that computer, it used to, you could see the dividing circuits, but all you could actually do is you could take the speed of the processor. So instead of using 2 clocks, we want them to synchronize. What they did is they just divided the speed of the processor, the clock feeding the processor, by a certain amount to get the speed of the I/O bus. So this is done now by what we call a chipset. So what I'm going to do is I'm going to connect this circuit right here. But over here, this is still, I'm going to leave this alone. This is just this guy right here. But I'm going to take the output of this flip-flop 1 and feed it into the input 2. We're not going to set it. We're not going to reset it. We got it set up to toggle. So to set it up for toggle, we bring J and K both to a 1. So I'm going to pause the lecture and go ahead and set this circuit up. So this is the circuit. And we can see that we've got a lot of stuff jumped on here because we're jumping out the presets and the clears and the J's and the K's on both flip-flops inside our 7476. Okay, I still have these hooked up, but that's, you know, but notice they're still flashing extremely fast because they're blinking so fast. Okay, what we're going to do when we go down to our clock signals is what I'm going to do is I'm going to show you a Q1, the output of Q1 first. So we've only got a 2-channel scope, so we need to reference this according to according to the clock input. So what we're going to do is we're going to go down here, and I still have it set up to look at the output of latch number 1. Okay, which is either pin 15 on latch or flip-flop 1 or pin 6 on flip-flop 2. I think I have it hooked up to 15 because it's on the same side as 11. So we're going to move back over to our scope. So I'm going to pause the lecture and set it. So this is our scope output for the first one, and this is output of latch number 1, which is between pin 15 and pin 6. So here's my input, here's my logo and edge, okay, and here's 1 cycle, which is 100 microseconds. Here's 1 cycle of output 2, output 1, which is 500 microseconds, and we did the math. So this right here, so the reciprocal of 100 microseconds is 10 kilohertz. The reciprocal of 200 microseconds is 5 kilohertz. So go ahead and just pause your lecture right here, and this will stay up here while you come in here and draw this. So it should be identical to the one you drew up in figure 16-7 for the Q1 output. The Q1 output should be identical to your figure 16-7. And this is where we messed up, guys, when on the group that was there on Wednesday. This is where we was having a little problem when we rewired the circuit, but it was getting late and I was getting tired. So I don't know what I did wrong, but it appears to be working perfect now. Okay, so now that you got that drawn, and like I said, you could pause the lecture and draw it, take your time, and then as soon as you get that, then unpause it. And now what I'm fixing to do is I'm fixing to move over to pin 11, which would be the Q2 output. So I'll take my scope probe and move it over to pin 11, 9, 10, 11, and this is our output now. So when we notice this, my input, 1, 2, so this is 1 cycle right here. Okay, and maybe this won't freeze, but even if it does, it'll be okay. So I'll be able to draw on the screen now, and I'm going to do it in red so we can keep it up. So this is cycle number 1. This is cycle number 2. This is cycle number 3, and then this is cycle number 4. Okay. Here our cycles start on the rising edge. Here our cycles start on the falling edge. So this right here would be 1 cycle of output Q2. Notice it took 4 cycles of the input for 1 cycle of the output, And guys, that is a divide by 2. But we can go ahead and do this. So this is 100 microseconds. This is 100 microseconds. This is 100 microseconds. And this is 100 microseconds. So that's 400 microseconds. Of course, I could have counted 50, 100, 50, 200, 50, 300, 50, 400. Because we have it on 50 microseconds per division. If you can't see that, this says 50 microseconds. Dot 0 microseconds. So that's 400 microseconds on the output, right? So up here, every one of these is 100 microseconds for a cycle up here. Okay. So what we're going to do is we're going to go ahead and move back over to our calculator to make sure that this thing is dividing by 4. Okay. So that means that we should calculate 250 microseconds, which would be which would be 10 kilohertz. I'm sorry, 250, 2.5 kilohertz, which is 10 kilohertz divided by. Let me bring this back. So let's escape and see if it comes back to us. Okay, sure does. So I'm going to bring my calculator back up, and we're going to do the math. So we had 100 microseconds on the input. Okay. So 100 microseconds times 10 to the negative 6. We know that is, I need to take the reciprocal, a reciprocal, which is 10 kilohertz. Okay. And then our second one took 200 microseconds. So if I was to take 10 kilohertz, I'm going to clear this. If I was to take 10 kilohertz, and then I come up here and divide that by 2, then that would give us 5 kilohertz. And if I divide that by 2 again, then that would give us 2.5 kilohertz. So what we did is we calculated, when we come over here on our screen, we calculated 400 microseconds. So let's do the frequency measure on our scope. 400 times 10 to the minus 6. And we'll take the reciprocals. Oops. What did we come up with? Undoubtedly, I messed up. I don't know what I was doing wrong a while ago, but 400 microseconds, which is what we measured, right, times 10 to the minus 6. We'll take the reciprocal of this, and it's 2.5 kilohertz. So that would be a divide by 4. And if I add another JK flip-flop, that would be a divide by 2. I'm sorry, that would be a divide by 8. So we come up here and add these things, and this is going to become very important, because what I'm fixing to do now is show you what we just made is we've made a 2-bit binary counter. And I'm going to pause the lecture and set this up for this. And what we're going to do now is we're going to look at the LEDs. And then I'll go on this and show you, I'm going to bring up PowerPoint. And I'll do that right now before I pause the lecture. So what I'm going to do is so what I'm going to do is I'm going to come over here and I'm going to take it off my 10 kilohertz clock. And I'm not going to draw the JK inputs, guys, because they're all connected to one. And just to make it easier. And then what I'm going to do is I'm going to take this back over here and I'm going to hook it up to one of my pulse switches. And this is going to be number 1. And then I'm going to take the Q output here and I'm going to bring this into my clock inputs of my second one. So this is number 2. This is the Q output. And we're not looking at the not Q, but I'm going to rewire this just a second to show you it's really cool. Now what I'm going to do is I'm going to take the Q output here, and I'm going to swap these around because they're backwards. And I'm going to bring this into light number 6. And then what I'm going to do, and normally in drawing we don't draw crooked lines like that. So what I'm going to do is I'm going to bring this output, and I'm going to bring this into LED number 6. And I'm going to take this Q output right here, and I'm going to bring this into LED number 7. And I'm going to hook this back up to the switch. And then, so I'm going to pause this and show you what this is going to do. And it is really, really neat. So I had the circuit that I wired up or connected in the last one. But what I did, like I said, is I took the Q output of 1 and I hooked it up to LED number 6. And then I hooked the Q of 2 and hooked it up to LED number 7. So I want you to watch this, and I've rehooked it back up to my pulse. So what I'm going to do is, if I was counting, that would be a 1, that would be a binary 1, that would be a binary 2, that would be a binary 3, and of course now it's going to roll back around. Binary 1, binary 2, binary 3. So JK flip-flops are counters. So if I hooked up another JK flip-flop, it would count to 7. If I hook up a 4th one, then it would count from 0 to 15. But it's also a divisor. So when we get into our counters, which is our main lecture, our next main lecture, and it'll probably be the last thing that we look at this semester. These guys are the bases. JK flip-flops are the basis of all our counters. These are count ups and count downs. And then I'll show y'all, if we couple the not Qs, the dang thing would count down. If we couple the Qs over to the next one, the next thing will count up. So basically we have two broad categories of counters. We have binary counters, and then we have BCD counters that would count from 0 to 9. And then they use internal AND gates to automatically reset it. And then we have what we call up-down counters, which we have the ability to tell the counter to even count up from 0 to 15 or down from 15 to 0. Then the counters has carries and borrows, so we can string these counters together. So most of our counters, basic counters, only count 4 bits. But what we have is we have a carry and a borrow that we can carry over to the next counter. So if I had 2 4-bit counters, just up counters, then we could count from 0 to 255. If we had 3 of them, then we could go from 0 to 512. 4 of them would be to 1024, and on up the line. Then we can look at some true counters that actually, I'll show y'all some counters that has the ability to count quite a few bits. So that's the next thing we're going to look at is counters. But all counters are just coupling JK flip-flops together inside the IC, and these guys count. Ain't that cute? Ain't that neat? So 0, 1, 2, 3, and then it will roll around. But when this one rolls around, what it would do is it would feed the Q output of this guy would feed the next guy, right? You understand that, and so on and so forth. So this is what we're going to talk about next. This concludes the lab, which will be lab 16. But you're going to have to answer your questions. So a lot of weight's on the questions within the lab, and also your drawings. A lot of weight's on the drawings. A lot of weight is doing your pin out on your circuits, how we connected them. And I told you which latch inside there or flip-flop we were using in our diagram. I told you which switches we were using. That should also be labeled. You should have your truth tables that we went through, and then of course And then on the test guides, it's going to be, you know, how to set and clear JK flip-flop. We're going to talk about synchronous inputs and asynchronous inputs. So you need to get that straight. So probably Monday we'll lecture on counters. Then hopefully we'll get through in a time so we can do the lab on counters. And then what we'll do is we'll let you turn you loose and let you and your team member go back and try to finish up the labs that you were working on before we started doing class labs. You still really need these hands-on. You can see, though, it looks like a lot of wiring, guys, but if I was to drop all the way back into transistors, and I think I told you about the post mill, the milling machine that I worked out on Beaches, out at Beaches Machinery out in Fairfield. That machine was old, and everything inside that was nothing but transistors. And it had hundreds of transistors, and it had like big circuit cards. The cards probably were 2 feet by 1.5 feet, and it was just totally loaded with transistors. And I can't remember how many cards was in there. I think it had, seems like it had 8 axes, and there was one card with counters and everything for each axis. So that's big circuit cards, and there must have been, good gracious, 200 transistors on there times 8. That would be, you know, that would be a lot of transistors. What, 1,600 transistors, and we could have came in there and replaced them. And I think I told y'all I replaced one of the counters. This thing was looking at right here. No, I'm sorry. I replaced one of the comparators that was done with nothing but transistors. I replaced it, and I can't remember how many transistors it was, but I replaced it with a 7475 and just wire wrapped it and put it on that board, and I guess it was still working because you could not get the parts to replace it. But luckily they had the diagrams. But they were big size D diagrams, but I wish I would have had the ability to copy those things so you could just see and compare it to what we do now with what we've done. Now, what we do with microprocessors, this logic, by the way, is ran by programs. But what you'll find out, and this is what I'm trying to stipulate, replacing hardware with software is nice, but software will never, ever, ever be as fast as the hardware that would replace it. So the hardware, the actual physical components, instead of doing it with software, with the physical components would be a lot faster. And so that's the end of Lab 16. What I'll do for the people that was in class on Wednesday is inside the write-up, I'll find out where this section starts, so you can go directly to this section to finish up the lab. Of course, for the people who was not there, then you're going to have to do the whole lab, like I said, and I'm going to send out a text to make sure you know that, and this is due on Monday at the start of class. Hope you have a great Easter, and this concludes this third section of the